Hello, my name is Julie Velandia, and I'm gonna talk to you today about my findings on Project One. I'm gonna explain to you my findings based on my implementations of RSA square multiply, RSA square multiply with the Chinese remainder theorem, random false attack, and timing attack. For the RSA square multiply, for my implementation, I used C++ and the NT and implemented the NT library. Um, Using the NT library was not easy, mainly because you have to compile it and you have to um, include your file to the your project file, install the references, and include the include folder with all the header files and all the files from the NTL library. Because if you do it outside of the project, then it doesn't work. You can't call it. Um, and then you have to make sure that the path that you're using to include those files is where those files are within your computer, wherever you saved it. Point is, it wasn't easy. But I learned with the square multiplied after implementing it that the way it works is that you generate two random prime numbers, p and q, then you calculate n, which is p times q, then you calculate your phi of n, which is p minus 1 times q minus 1, and then you calculate your value, your public key E value, and then encode your message as your message to the power of your key value E modular N. And then to decode your message, you calculate your value of D, which is e to the minus 1 modular N, and then you decode your message as M is equal to your encoded value C to the power of your private key D modular N. I also learned that it takes time to complete these calculations, mainly because the numbers are huge. So, and the bigger they are, the longer it takes. Now I'm going to talk about RSA square multiply with the Chinese remainder theorem. So I learned that the way it works is that for encoding the message is pretty much the same as square multiply without the Chinese remainder theorem. And the one what changes is how you decode the message. So instead of you decoding the message as your C encoded message to the power of your private key value D mode N, you do C to the power of your key value D mode P first, which is the factor of N, and then mode Q after, which is the other factor of N. And then the way it works is that the Chinese remainder theorem would simplify these values to smaller, easily calculable values, and then it would combine both of these to provide your message, to produce the message. Um, in my implementation, I also use the NTL library and C++. And also difficult because it was the first time I worked with the Chinese remainder theorem and with the NTL library. So, I mean, if I had a hard time implementing the square multiply without the Chinese remainder theorem, imagine the Chinese remainder theorem. Um, so in my findings, I found that RSA with the Chinese remainder theorem is by far faster than RSA square multiply, and I found it to be approximately 5 to 10 times faster, and this is due to the size of the numbers to which the square multiplied happens. And the reason why is because the larger the numbers, the longer it takes to compute these values. But with Chinese remainder theorem, because these values are simplified and then combined together to produce the message, the more simplified and the more simpler the numbers are to calculate, the faster it is to obviously do the calculation. And therefore the less time it would take to do this calculation. Talk about the random false attacks. So with my implementation, I learned a couple of things. The first one is that the purpose of the RSA fault attack is to, design a false signature that would find a factor of n that would allow you to find the other factor of n and decode the message. Because once you find the factors of n, then you can decode the message. In my implementation, I wasn't always able to get the message back, and I know that I made a mistake somewhere. I just don't know where my mistake is, and since I've never done fault attacks, I did my very best to kind of make it work, but again, I don't know where my mistake is. I'm pretty sure I can find it if I just take the time to go through it, but yeah. But I also learned that the security of the RSA crypto system relies on the hardness of two-factor n. If it is almost impossible to find a factor of n, then it is almost impossible to decode the encrypted message. I also learned that the strength of RSA comes from the fact that factoring very large numbers is difficult, and the best known methods to do this are all still very slow. Um, yeah. Lastly, I'm going to talk about the timing attack. This is so below you can see the kosher algorithm, which sets z equal to your m message value and then c to 1. And then for the values of I to n, it would check to see if this one, and if it is, I will set c equals to c times the z mod n modular n, and then it would set z equals to c to the power of the public key e modular n. And at the end of the whole process, it should provide you it should provide c as a value that goes m your message times the private key d modular n. In this attack, I learned that the purpose of the attack is to find the private key d. That the time that it works as follows. The attacker will complete the equation of c to the d, c to the private key d modular n for different selected values of c, not calculated, selected values of c, by measuring the time it takes to complete it each time and analyzing the different time variations. So basically, the attacker will find d one bit at a time over a specified period that is obtained by the number of bits in d. Also, I learned that since RSA modular operations are usually a very large number raised to another very large number, this process is time consuming. And I learned that there were two algorithms that you could implement to do these modular operations in a more simple and efficient way. And one of those algorithms being the Montgomery algorithm. And the reason why it is used to do the square multiply within RSA as well as the Chinese remainder theorem, it is because the Montgomery algorithm maintains the time to compute these operations constant, no matter the size of the factors. So it could be the biggest factor when you could ever think of, and the time would still be constant. And then obviously you have the second algorithm as the Chinese remainder theorem, which instead of keeping the time constant, it would just reduce the time that it takes for all the modular computations to occur depending on the size of the values of the factors of n. In my implementation, I wasn't able to fully obtain the message per se. So and the one time that I did, I know I made a mistake somewhere because it seemed to have skipped a step within the program. But again, I try to go over it and like see where the mistake was, and I couldn't find it. So but yeah, so this were my findings on our project one, and thank you so much for listening.